Once again, I welcome you all to another video lesson. Today we shall be discussing some more topics from the chapter Kinetic Theory of Gases. Let's begin today's discussion with the topic degrees of freedom. What is the meaning of this term? What is degrees of freedom? The degrees of freedom of a system are defined as the total number of coordinates or independent quantities required to describe the configuration of the system completely. Now, what does that mean? Let us consider a system comprising of n particles. So, for a system consisting of n particles, if the particles possess k independent relations between them. Now, what does that mean? Depending upon the number of particles, suppose we are talking about the position. Where are the particles present inside the system, and what is the distance between these particles? So, how many independent relations exist between the particles? So, if we denote that with k, so if the particles possess k independent relations between them, then the number of degrees of freedom of the system is given by this expression. F stands for degrees of freedom. So that is equal to 3n minus k, where n is the number of particles in the system and k the number of independent relations between the particles. So this expression f equal to 3n minus k will give us the value for degrees of freedom for a system. Now this will become more clear when we discuss some examples. Let's begin with the monoatomic gas molecule. Now, how many atoms are present inside that molecule? Obviously it is monoatomic, so n will be equal to 1. If there is only one molecule, then k, that is the number of independent relations, will be equal to 0, as there is only one particle. So f, that is equal to 3n minus k, will be equal to 3 into 1, n is 1, minus 0, k is 0. So 3 into 1 is 3, 3 minus 0 gives us 3. Therefore, a monoatomic gas molecule possesses 3 degrees of freedom. Coming to diatomic gas molecule, there are two molecules, okay, and these two molecules are held at a fixed distance by the molecular bond. So this is the bond existing between the two particles. So obviously number of particles is 2, and how many independent relations are there? 1. So k is equal to 1. So now from the formula of degrees of freedom, f equal to 3n minus k, that will give you 3 into 2, n is 2, minus 1. So 3 into 2 is 6, 6 minus 1 is 5. So a diatomic molecule has 5 degrees of freedom. Coming to triatomic gas molecule. Obviously number of molecules, number of particles in this molecule is 3. So 1, 2 and 3. Now there may be two different kind of arrangements. This is a non-linear arrangement and this is a linear arrangement. So in case of a non-linear arrangement, you can see there are 3 independent relations. So n is equal to 3, number of particles is 3, and k 1, 2, 3. So k is also equal to 3. So degrees of freedom f will be equal to 3n minus k, that is 3 into 3 minus 3. So 9 minus 3, that will be 6. But for a linear arrangement, n is equal to 3, k is equal to 2, 1, 2. So f is equal to 3n minus k, that is 3 3s are 9, 9 minus 2, that is 7. So depending upon the number of particles and the kind of arrangement, we can decide the degrees of freedom. So in case of a triatomic gas molecule, depending upon the type of arrangement of the particles, we can have different degrees of freedom. So now this is one way of deciding the degrees of freedom, but there is another way too. A collection of gas atoms or molecules in a vessel is a thermodynamical system. The gas atoms or molecules are in random motion and possess energy due to their different types of motion. So, the degrees of freedom of a system can also be defined as the number of independent modes of absorption of energy by the particles of the system. The degrees of freedom of a gas molecule can be determined by knowing the number of ways in which the gas molecule can absorb energy. So now when we are talking about energy, the gas molecules can have different types of kinetic energy. So the energy possessed by the gas molecule could be kinetic energy of translational motion. So gas molecule possesses kinetic energy of translational motion due to its linear motion. Okay, linear motion. So this is given by Et equal to half mv square, where v is the linear velocity of the gas molecule. Then it could be kinetic energy of rotational motion. The kinetic energy possessed by a gas molecule due to its rotational motion about an axis is called its rotational kinetic energy, and it is given by E r equal to half I omega square, where if the gas molecule is treated as a point mass, then I is equal to 0, and hence such a gas molecule cannot possess kinetic energy of rotational motion. It is true even when the gas molecule may actually be possessing rotational motion. However, for a diatomic gas molecule, moment of inertia may not be 0, and therefore such a gas molecule can possess kinetic energy of rotational motion. The third is kinetic energy of vibrational motion. A gas molecule possesses kinetic energy of vibrational motion when it vibrates about its mean position. The vibrational motion gets excited only at very high temperature, maybe above 5000 Kelvin, and hence at ordinary temperature of the gas, a gas molecule may possess kinetic energy of translational and rotational motion only. Now, it will be worthwhile to again calculate the degrees of freedom of a monoatomic and diatomic gas molecule according to this definition of degrees of freedom. So let's begin with monoatomic gas molecule. Now, you can see that a monoatomic gas molecule can absorb kinetic energy of translational motion along each of the three axes, x, y and z, and hence possesses 3 degrees of freedom corresponding to translational motion. Now, as the monoatomic gas molecule is considered to be a point mass, so it cannot kinetic energy of rotational motion and hence does not possess any degree of freedom corresponding to the rotational motion. So, we may say that degrees of freedom of a monoatomic gas molecule is equal to 3 plus 0, that is equal to 3, which is the same as we had calculated earlier. Next is diatomic gas molecule. Now refer to this figure where you can see a diatomic gas molecule lying along y-axis. It has a non-zero value of moment of inertia about the axis OX and OZ, but moment of inertia of the molecule about the axis OY will be 0. Hence it will possess 3 degrees of freedom corresponding to its translational motion, corresponding to each mode of absorption of translational energy along OX, OY and OZ, and 2 degrees of freedom corresponding to its rotational motion, corresponding to each mode of absorption of rotational energy about OX and OZ axis. Therefore, degrees of freedom of a diatomic gas molecule, that will be equal to 3 plus 2, that is equal to 5. And this is again the same as calculated earlier. Now, at very high temperatures of the order of 5000 Kelvin, the vibrational motion excites up in the gas molecules. Then the diatomic gas molecule possesses 3 plus 2 plus 2, that is 7 degrees of freedom. The additional 2 degrees of freedom being due to its vibrational motion. Now here I would like to point out that the molecules of chlorine gas possess degrees of freedom due to vibrational motion even at room temperature. Let's now study about the law of equipartition of energy. What does it state? It states that for a dynamical system in thermal equilibrium, the energy of the system is equally distributed amongst the various degrees of freedom, and the energy associated with each degree of freedom per molecule is half kT, where K is the Boltzmann constant. Now, let us consider 1 mole of a monoatomic gas in thermal equilibrium at temperature T. Now, each gas molecule has 3 degrees of freedom due to its translational motion. So, according to kinetic theory of gases, the mean energy of translational motion of a gas molecule is given by half mv bar square, that is equal to 3 by 2 kT, where v bar square is the mean square velocity of the gas molecule of mass m. Now, if Vx square, Vy square and Vz square are the components of V bar square along the 3 axes, then average energy of a gas molecule will be half m v bar square equal to half m vx square plus half m v bar y square plus half m v bar z square. So now we may write from the previous case, we may write down half m v bar x square plus half m v bar y square plus half m v bar z square to be equal to 3 by 2 kT. Now, the molecular motion is random in nature and no direction of motion is a referred one. Therefore, the average kinetic energy corresponding to each degree of freedom is the same. Therefore, we may write down half m v bar x square to be equal to half m v bar y square, and this is equal to half m v bar z square. Therefore, from the above equation we get half m v bar x square equal to half m v bar y square equal to half m v bar z square to be equal to half k T. Thus, the mean kinetic energy per molecule per degree of freedom is half kT. This result was first deduced by Boltzmann. Now, let us find out the specific heat of a monoatomic and diatomic gas. Consider 1 mole of a gas. Let each gas molecule possess F degrees of freedom. Now, as 1 mole of the gas contains n molecules, total degrees of freedom of the system should be equal to how much? N F. If T is temperature of the system, then by law of equipartition of energy, amount of energy equal to half kT is associated with each degree of freedom. Therefore, total energy of the system U will be equal to NF into half kT, that is equal to F by 2 RT. Here N into K is equal to R. The gas constant for 1 mole of gas. Now, the molar specific heat of the gas at constant volume that is Cv. This is equal to du by dt. So this is equal to d by dt, and let's substitute the value of u, that is f by 2 RT. So therefore Cv comes out f by 2 times R. We also know that for an ideal gas, Cp is equal to Cv plus R. So this will be equal to f by 2 R plus R. Therefore Cp is equal to 1 plus f by 2 times R. So this is the molar specific heat of a gas at constant pressure. Therefore the ratio of the two specific heats, gamma, that is Cp by Cv, that is equal to 1 plus f by 2 times R divided by value of Cv is f by 2R, which implies that gamma is equal to 1 plus 2 by f. So this is the general expression for ratio of specific heat. Now we can calculate for monoatomic and diatomic gases. First of all, for monoatomic gas, we know that for monoatomic gas F is equal to 3. Therefore Cv will be equal to 3 by 2 R, that is equal to 3 by 2 into 1.98, that is 2.97 calorie per mole per Kelvin. Cp, that will be equal to 1 plus 3 by 2, that is into 1.98, that is equal to 5 by 2 into 1.98, that is 4.95 calorie per mole per Kelvin. Therefore gamma will be equal to 1 plus 2 by 3, that is equal to 1.67. This is for a monoatomic gas. For diatomic gas, F is equal to 5. Therefore Cv is 5 by 2R, that is 5 by 2 into 1.98, that is equal to 4.95 calorie per mole per Kelvin, and Cp will be equal to 1 plus 5 by 2 into 1.98, that is 7 by 2 into 1.98, that is equal to 6.93 calorie per mole per Kelvin. Therefore gamma is equal to 1 plus 2 by 5, that is equal to 1.4. In this way we can do the calculations for different types of gases. That will be all for today. Thank you.